In this lesson, we talk about what's called sinusoidal functions, so we'll start right off with the definition. So sinusoidal functions are functions that are transformations of y equals sine of x and y equals cosine of x. So they either have sine or cosine as the operating function. So we'll start off again talking about amplitude. And amplitude is represented by a capital A. So we would have a capital A in front of my sine or cosine function. Y equals a sine of x, y equals a cosine of x. And amplitude, you have to remember, is always positive. So even if there's a negative sign in front of it, we always want to take the absolute value of whatever you see. Because a negative sign, that's really a reflection. You should know that from our transformation unit. And the amplitude is the same as a dilation, a vertical stretch or shrink. So we're going to show that by sketching these two functions, y equals 2 cosine of t and y equals negative 2 cosine of t on the same axis. Now when we sketch, this is like the sketches you're going to see in the FLCC book. I don't have a grid. I'm going to make my own grid here, and there are different ways to sketch trig functions. In this example, we're going to start with an x and y axis, starting at the origin, and I'm going to put a tick mark at every pi over 2 measurement. So we have pi over 2 and pi and 3 pi over 2, and I'm off just a little bit in the scale, so you'll have to excuse that, and 2 pi. So that's my t-axis. This is my y-axis. If I start off with 2 cosine of t, it's the standard cosine curve. The cosine curve is this guy. He starts up at the maximum, only now he's going to start up at 2, and his minimum is negative 2. He's going to cross the t-axis in the same spot that he always does. He crosses at pi over 2 and at 3 pi over 2. So he's at maximum, which is 2, and then he crosses here, and then at pi he's at his minimum value of negative 2, and he crosses, and he's back up again. To sketch negative 2 cosine of t, the only difference is the negative sign, and this acts as a reflection over the t-axis. And that should be reviewed, everybody. So instead of starting at positive 2, he starts at negative 2, and then he increases a maximum at pi, and then a minimum at 2 pi. So that's what it looks like. The blue is negative 2 cosine of t, and the red is 2 cosine of t. You'll have to excuse how squiggly my line is. It's supposed to be a smooth curve, but it looks like that's not happening today. And then again, as a review, the midline, that is the line y equals k. So it's a horizontal line, and it's going to split. It's going to go right down the middle. It's halfway between the min and max. So that's a vertical shift. For my sine function, if I have an amplitude of a, then I have the sine of t. I'm going to add k to the outside of that function, so I'll put parentheses there just to make sure. And for the cosine, same thing, cosine of t plus k. When k is positive, it shifts up. When k is negative, it shifts down. The third thing we're going to talk about is the period length of the function, because these are periodic functions. They repeat after so many radians or degrees. So we're going to define that. So the period is essentially applying a dilation inside the function, our vertical stretch and shrink. We just talk about it in different terms when we talk about sinusoidal functions. And the standard notation, I believe, in both of your books, A is the amplitude, and then we have sine. Capital B, the coefficient in front of the independent variable. The capital B is how you're going to find the period length. It's not the period length itself, but we're going to get there using this coefficient in front of the x value. So we have y is equal to a cosine of capital B, x. Here's how the period length is defined. For either sine or cosine, we know the standard sine or cosine curve completes 1 cycle and 2 pi radians, or 360 degrees, 2 pi radians. So the period length is going to be 2 pi divided by the coefficient in front of the x, the b value. So the B is really the number of cycles in 2 pi. Okay? It's how many times it repeats itself within the 2 pi period. Because when the coefficient is 1, that makes the period length 2 pi, which is the standard period length. So you're going to have some examples of finding the amplitude in the period. The first example is y equals -2 cosine of 3x. So you take a minute and write down what you think the amplitude and the period length is. And when you do that, you got to remember the amplitude is positive, so if you thought -2, you were not correct. The amplitude is 2. The negative implies a reflection, but the amplitude is 2. The period length is going to be 2 pi divided by 3, because the b value is the 3, it's the coefficient in front of the independent variable. Alright, take a look at the next one, y equals 5 times the sine of 1/2 x. Pause the video, write down what you think the amplitude and the period length is. And then when you come back, you should get that the amplitude is 5. This time, the period is going to be 2 pi divided by 1/2. So that ends up being 4 pi. Because you're only going through half a cycle in 2 pi radians. So this one's going to be really stretched out. Remember, inside the function, it behaves counterintuitively. 1/2 is actually a horizontal stretch, which makes the period 4 pi. Now we're going to work backwards. We're given a function. I'm telling you which one it is because it could essentially be both, either sine or cosine. And we're going to find a formula for it. So if I look at this, look at the starting point. It starts at 0, 0. And that's the standard sine curve. The standard sine curve, I call it the barrel of monkeys. Looks like that. So that's good. The midline is centered on the axis, so the amplitude is going to be the distance from midline to max. That's going to be 3. So we write that down. We got an amplitude of 3. This looks like the standard sine curve, so there is no reflection. I start at the center and I increase. So the only other thing I need to get, since the midline is 0 and there is no reflection, is the period length. Well, I have to mark this better. This is actually in radians, but it's not in terms of pi. This is 2 pi, and this ends up being 4 pi. So the period length is a direct read of the graph. If I look at this, I'm all the way out to 4 pi. So the period length is 4 pi. That's not what I put in the function, though. What I have to do is find the b value. So if I know that the period is 2 pi divided by the b value, if I were to cross multiply that and solve for b, it's a similar thing. b is 2 pi divided by the period length. So in this case, b is going to be 2 pi divided by 4 pi, which is 1/2. If your period length is in terms of pi, your b value will not be in terms of pi, and vice versa. So my final answer here is y is equal to 3 times the sine. Let me fix that. It looks messy. 3 times the sine of 1/2 t or x or whatever you want to call it. There you go. This next example I'm going to leave for you to figure out, and then we can talk about it in class. And then the last thing we're going to do, and then we'll finish up in class, is talk about the phase shift. And we'll spend more time on that tomorrow because the phase shift can be a little bit tricky, so I just want to quickly define it here. My function with the phase shift looks something like this. If it's a sine function, I have an amplitude and then the sine of my b coefficient, and the phase shift is going to be any horizontal shift you have, minus h. Again, it's counterintuitive, but this tells me that my whole thing is going to shift by h units to the right. In order to correctly read this, my b value has to be factored out. Okay? So we're going to deal with that tomorrow. I just wanted to kind of introduce it today. So my function could look like this, and I can always add a midline shift on that, on top of that. My cosine function would be the same thing. A times the cosine of b times t minus h plus k. So we're going to look at all that tomorrow and practice graphing these things over the next few days.